Okay, so after discussing the heat flux, let me now talk about the energy transport by convection. Okay, now on your screen, what can you see? Bolo. Okay, let me clarify. So, what I am doing right now, I am talking about convection, right? So, basic topic is convection. Okay, so here you see what you can see on the screen right now, or what I want to convey is, let us start by imagining a blob. Blob means some fluid part is there, some liquid drop or something, a blob. Okay, blob of matter. Let us consider this. Now, this is present in presence of gravity also, because I want to talk about what is happening inside the star. So there is a gravity here, and I have got a blob of matter as well. Now, so I ask you to imagine a blob of matter in a gravitating fluid, and that is displaced upward. You see, which is displaced upward. That means the gravity is this side, and this blob of matter, it is slowly moving upward. It is displaced upward. Now what can happen? What are the possibilities of this displacement? This is what you can see in the screen. The possibilities as a result of this displacement. Okay, so there are basically three possibilities. Number one is this, or number A. What is this? You see, if the region is convectively stable, then what will happen is that the displaced blob experiences a restoring force. So this is a convective motion, so the blob is moving. Right. Now, in case of there is a convective stability, then the displaced blob, what will happen is that it will experience a restoring force. You see, like this, there is sort of restoring force that tends to return it to its original position. This is the restoring force. So the blob is displaced, and then there is a restoring force, so it comes back to its original position, something like that. However, because of this overshooting, so when it comes back, there is a sort of overshooting, and because of this, the blob executes a stable oscillation. There is a stable oscillation, sort of like this, around an equilibrium height with a frequency, and that frequency is known as Brunt-Vasala frequency. Okay, so this is when the region is convectively stable, and this is the present case. So I am just displacing, and in case of convective stability, so stability and then comes instability. So in case of stability, it experiences a restoring force that tends to return it to its original position, but because of the overshooting, the blob executes a stable oscillation around an equilibrium height with a frequency known as Brunt-Vasala frequency. Now, you see, if the blob of the material at position 2 here is less dense, then what will happen? So what I am saying is, again, if the blob of material at position 2 here, when it is displaced, is less dense than the surrounding material, then what will happen is that it will be driven continuously upward by buoyant forces. Like this here. So actually, if you work out, then you will see that instead of oscillation solution, we will have a sort of exponential. And so what is happening is that if the, you see, blob at of material at position 2 is less dense than the surrounding material, it will be driven continuously upward by buoyant forces. And then what we will say is that the region is convectively unstable. Okay. Because it will goes on rising as time goes on. Now, based on this very basic idea, what we are going to do is that we are going to impose particular physical conditions on how the blob of matter is moving, and you will see that this leads us to 3 separate criteria for convective instability. Okay, and what are the 3 separate criteria? The first one is Schwarzschild criteria, next is Redux, followed by double diffusion criteria. Okay, now let us talk about the Schwarzschild criteria or Schwarzschild instability first. Now you see, suppose the blob, this is the blob, is moving adiabatically, right? So it moves adiabatically, which means constant entropy. So constant entropy. But you see, in both pressure and composition equilibrium with surroundings. So in this case, I am considering the blob which is moving adiabatically, but the blob is in pressure and composition equilibrium with surroundings. Now let us denote the pressure, the entropy and the composition of the medium at position 1. This is position 1 and this is position 2. Okay. Now at position 1 by PSC, so this is position 1 and this is position 2. Now let me denote pressure, entropy, composition in position 1 by PSC, and the same in position 2 with prime coordinates. P prime, S prime, P prime, S and C prime. Why there is no S prime? Because I am saying constant entropy. Okay, adiabatically. Okay, so now as we were saying, the region is unstable if you see the density of this part here, the density in this part outside region is greater than the density inside the region. Then what will happen? It will just move up and then there is instability. So we want instability to happen. That means we want this blob to move upward against gravity. So we are now trying to figure out ways of moving this blob against the gravity. And for that, what we just found is that the region becomes unstable. That means the blob moves upward if the density of this surrounding region is more than the density inside the blob, right? So basically the condition for convective instability is that the blob is less dense than your surrounding medium at point 2. So this is basically, you see, this corresponds to medium, density of medium, and this corresponds to density of blob. Okay, fine. Now this we are talking about at point 2, right? Now you see, if we do, now let us expand this density difference in Taylor series expansion. And if we do that, and if we keep only the first term of this, then we have this result. Okay. Now, what I am going to do, বলো
কমের জন্য উপরের দিকে যাচ্ছে তো এটা
হ্যাঁ এই যে দেখো আমি কি বলছি density of medium is more than the density of the blob, then only it will be moving upward. So basically if the density of the blob is less than the surrounding medium, একটা জলের ভেতরে জলের বালতির ভেতরে যদি আমি একটা বেলুন ছোট্ট বেলুন ফুলিয়ে নিচে রেখে দিই তাহলে বেলুনটা কোথায় যাবে নিচে ডুবে যাবে না উপরে আসবে উপরে আসবে কেন বিকজ হ্যাঁ কারণ because you see if as I'm saying if I fill in air inside a small balloon and I dip inside a bucket of water, then the density of the air inside the balloon is much lesser than the density of the surrounding water, and as a result the balloon will just move upward. This we know, children's play at home, even my small kid also plays such games. But this is so this is basically what I am saying. আমি ওই বেলুন খেলাই করছি অঙ্কের মাধ্যমে বেলুন খেলা সূর্যের ভেতরে যা হচ্ছে হ্যাঁ বেলুন খেলা হচ্ছে sort of, but this has got a fancy name, Schwarzschild instability. Okay, so now just what we did is we perform a Taylor series expansion. First term I am retaining. এবার দেখো what I am going to do is, okay, now I know this relation. What is the value of Cp? I am using thermodynamics. So using this I can write like this. So del rho del s is del rho del t del s, and so basically I can write del rho del s as del rho del t by tcp. What I want to do, I am thinking of how to write this expression. That's why I have introduced this Cp. So basically by using this Cp, now I want to introduce the heat capacity at constant pressure, that is Cp. Now after this we may exchange the entropy S for temperature T as variable. So after introducing Cp, now we are going to exchange entropy for temperature T as variable, and if we do that then our Schwarzschild condition becomes this condition. You see this expression, I am just putting the value over here. Now note this value, note that this value del t del rho del t, this is negative. So what does this mean? This means that this whole term must be greater than 0, but it is known that typically the value of del rho del t at constant P and C, composition and pressure, note that here I am using the value of C for composition, right? In this case also sometimes we use Xi as composition, but here I am writing C for composition. So if this term has to become positive, where this one is always most of the time negative, then what does this mean? What does this tell us about del S del R? It means that the Schwarzschild instability condition can be written like this. So this is the Schwarzschild condition for instability. Okay, del S ds dr is less than equal to 0. So we conclude that a region is unstable against Schwarzschild convection here if there is a negative entropy gradient. So you can see this is Schwarzschild unstable region. since there is a negative entropy gradient. Okay, this is very interesting. Now, so remember, we started out as we said that there are three conditions. Okay, so the first one was Schwarzschild, where we talked about constant S, then constant T. We use this condition. Okay, fine. And we arrived at this Schwarzschild instability condition. Let me now talk about the second criteria, or the Redux instability. Okay, now again, this time let us assume that the blob moves adiabatically with no composition change, but in pressure equilibrium with the surroundings. So previously we have what? Previously we have only constant S. This time we have constant S and constant C as well. Okay, as you can see in this figure. So similar to the previous case, you can say that the region is unstable if the blob moves up, and that will happen if the density inside is lower than the density outside. That means if the density at here, you see P prime SC, this inside is lower than the outside, and this is the outside density. So this is the convective instability according to the Redux criteria. Now again let us do the Taylor series expansion density and retain the first term. Upon doing that, so upon performing Taylor series expansion, you see this is what we get. Now you must remember this, realize this term. This is our previous term, and this was there because of assuming constant entropy or constant temperature. We assumed this, right? But this time this term is present because of constant composition. So as I was saying, the first term is as for Schwarzschild, and the second term arises because of the assumption of no composition change. Now usually you see both partial derivatives are negative. These two, they are both negative. This one is also negative and this one is also negative. And so this Redux condition, it takes a different form, and the form is like this: ds dr plus b dc dr is less than equal to 0. So if these two are negative, then we have got this type of condition. So this is the Redux condition. Okay, remember here that b is positive. B is a constant and it is positive. Okay. And here on your screen you can see that you can say that a region is unstable against Redux convection if both the entropy, here you see entropy, and the concentration variables, both of them have negative gradients. Then only we will have the Redux instability criteria. Okay. Now, if the entropy gradient here and the concentration gradient have opposite signs, then you see the stability of the region is dependent on the relative sizes of the two terms. So it is possible that we can have a situation like this, where one is like this, another is like this, or one is like this, another is like this, something like that. Then in this case we will have to consider this whole condition, not separate. So this is what I want to say, is that the stability of the region is dependent on the relative sizes of the two terms. Okay, because you see it is possible. So it is possible that a region could be Schwarzschild stable but Redux unstable. Okay, this is possible. So how will it happen? This will happen if the concentration term is more dominant, like that. So this can happen. Any questions till now? Okay. Now let me talk about the third instability, and this has got a very peculiar name: salt finger instability. Okay. Now what happens is that we will now consider a situation where the blob is in temperature and pressure equilibrium with the surrounding medium, but it is not in composition equilibrium. You see here, no composition equilibrium. Now the condition for the instability, what is this? Here you can see this is the condition. You see, you compare the two compositions, then only you can say the blob moves in temperature and pressure equilibrium. So this means both the same values but with the surrounding medium here, but not in composition equilibrium. So this is why you see the blob's composition is not the same as in surrounding composition here. So the condition for convective instability in this case will become just like this. The density here is lower than the density outside. So this is the outside density and this is the inside density. And again, if we do the Taylor series expansion, then our condition becomes like this over here. Now let me give you an example of this salt finger instability here. So let us consider the following thought experiment, which you can see in your figure, in which such an instability could occur. Now let us consider a layer of hot salt water that lies over a layer of cold fresh water. Okay. Now imagine a blob of hot salt water that begins to sink, go downward into the underlying cold fresh water. Now this blob of sinking material will be able to come into heat equilibrium with the surroundings faster than it will be able to come into composition equilibrium. Now why is this? This is because you see the transfer of heat by molecular collisions generally is faster than the motion of sodium and chlorine ions that causes the composition to equilibrate. And so such a blob may be in approximate temperature equilibrium but remain out of composition equilibrium. So you see that heat diffusion will cool the blob of salt water, and since salt water is more dense than fresh water at the same temperature, so what will happen is that the blob continues to sink. And as this motion continues, what will happen is that the medium will develop fingers of salt reaching down from the fresh water. So the result will be like this. You see, so result will be like this. Where this is your hot salt water, okay, and outside is cold fresh water. And so you see the medium develops these fingers, and these are known as salt fingers. Okay, now you see this salt finger instability, this is basically an example of a class of instability that are known as double diffusive instabilities, and they can occur when two diffusing surfaces, here hot salt water and cold fresh water is taken. So these double diffusive instabilities, they occur when two diffusing surfaces are present and one of the substances diffuse more rapidly than the other, and also the substance diffusing more rapidly has a stabilizing gradient and the slowly diffusing substance has a destabilizing gradient. So in this example here, the cold salt water is more dense than the cold fresh water. Okay, any questions? No more questions? You see, for stars, the most important convective instability is basically the Schwarzschild condition, which is ds dr is less than equal to 0, and it is driven by entropy gradients. Now this instability criteria for Schwarzschild convection, it can also be expressed, so you can see it can also be expressed in terms of a critical temperature gradient, and that is dt dr is less than dt dr adiabatic, and the value of this dt dr adiabatic is 1 minus 1 by gamma T by P dP dr, where generally both derivatives are negative in the inequality over here. Now, so you can say a region is convectively unstable if its actual temperature gradient, this one, is steeper than the adiabatic temperature gradient. So what we can say is that a region is convectively unstable if its actual temperature gradient is steeper than the adiabatic temperature gradient. Okay, let me show you what do I mean. So if this is the temperature and this is the radius, then you see something like this, and so you see this is dt dr adiabatic and this one is dt dr actual, and this is an example of basic convective instability. So you see, what you can see here is that the critical temperature gradient, which is the solid line for convection, and in this example the critical temperature gradient, in this example this is actual temperature gradient, which is basically this dashed line, and this is the adiabatic or critical one. So this actual temperature gradient is steeper than the adiabatic gradient. So this region is convectively unstable. Okay. Okay, so let me show this derivation to you before I conclude my today's lecture. Okay, so you see, for this alternative version, this is, you can say, a different version of Schwarzschild condition. What we will do is we will assume a blob of surrounding medium. So let me show you again. This is gravity downwards, and this is at radius r, and this is at radius r plus delta r, and here again we have the blob, temperature T, pressure P, density rho. Now this blob is moving upward, so this means there is convective instability, and here the temperature inside is this P plus delta P and rho plus delta rho. What about the medium outside? Here in the outside medium the temperature is this, pressure is this. Notice these differences inside and outside. What about here? Here the temperature, pressure and density are the same. So we are assuming a blob and a surrounding medium of uniform composition. Here uniform composition. Okay, with the blob in equilibrium with the surrounding at radius r. Now what happens if this blob is displaced to r plus delta r is what we have shown. Now in accordance with the Schwarzschild condition, the blob is assumed to be in approximate, not always, to be in approximate pressure and concentration equilibrium, so that you see delta P is equal to this del P, and it is assumed that the time scale for vertical motion of the blob is sufficiently fast so that little transfer of heat occurs between the blob and the surrounding medium as it rises from R to R plus delta R. So this means adiabatic conditions. So we are having these three important sort of conditions, right? Now for an adiabatic ideal gas, we have, you see, P is proportional to rho to the power gamma. So from this we have del rho by rho is equal to 1 by gamma del P by P. Okay, so you see the blob will continue to rise to R plus delta R if what? So let me write it down. So the blob will continue to rise at R plus delta R if this change is less than this change, right? If its density over here is less than this outside. So notice this. And since it will be buoyant in the surrounding medium, thus convective instability is implied if you see rho by gamma del P by P is less than grad P. Okay, here I am using the previous expression. Okay, now from ideal gas law we know that which may be combined with this equation, and when we can combine these two equations, what we will have is this relation. Okay. Now let us assume that these two are equal, and then reverting to differential notation, the condition for convective instability, we can write it as, you see, dt dr is less than 1 minus 1 by gamma T by P dP dr. Okay, so you see this was the initial condition which we mentioned over here. So we are now at the end of our class. Any more questions? আমি এটা বানাচ্ছি, I am just preparing. Any questions? Probably you have learnt a lot more today regarding the various convective instabilities. They are very interesting. They are very pictures diagrams, I think. So there are no more questions then. Good.